Okay, so I think we've got a good crowd here today. Get going for Vicky's talk today. So she's actually here finishing up her Helen Sawyer Hogg internship that I guess was started in the springtime and coming and finishing it up. So for people who don't know, Helen Sawyer Hogg was a Canadian astronomer that worked on variable stars and globular clusters, and this visitorship was in order to bring distinguished female scientists to UT, and this award is given out every 3 years. So this year we have Vicky Kaspi here with us from McGill University to talk to us about the hunt for radio pulsars.
Well, thank you very much. It's a pleasure to be back here again. And I'm going to talk to you about radio pulsars. Get right going. Overview of the talk. I don't think I have to give a very detailed introduction to what is a radio pulsar here, but just to be sure we're on the same page, I'll describe them, and then I'll first of all motivate why we're doing a lot of work in searching for more radio pulsars. Why do we want to find more of them? I'll tell you how we go about finding them. Actually, I really enjoy the process. I find the hunt really exciting, and I'll tell you how we do that. And I'll describe current pulsar surveys, two that I'm heavily involved in. The PALFA Survey, that's being done at the 300-meter reflector at Arecibo, Puerto Rico, and the Green Bank North Celestial Cap Survey. If I have time, I'll talk to you about that one too. So first of all, radio pulsars. You probably know all of this, but just briefly, these are rotating magnetized neutron stars. We know currently about 2,000 of them in the galaxy, and we know a few of them in the Magellanic Clouds. But that's it. They are relatively weak radio sources. In principle, people often ask me this, you could detect one in Andromeda if you knew the period in advance, if you took the most luminous known pulsar and stuck it there. But anyway, currently everything we know is in the galaxy or the Magellanic Clouds. They emit across the electromagnetic spectrum. So they are very broadband sources of pulsed radiation. Although today I'm going to talk only about the radio waves. The other stuff is interesting too, but here today is a radio day. All of that emission that we see across the spectrum from radio to gamma rays is powered by spin-down at these sources. So they are highly magnetized, and the rotating magnet emits radiation, and so the source slows down with time, and that loss of kinetic energy is the ultimate power for the radiation that we see in these sources. The periods, the rotational periods we see in these sources, I'm going to show you distribution shortly, but just to start out the conversation, currently this is the known range, 1.4 milliseconds, so that's the rotation rate of the neutron star, up to the slowest one we know of is about 8 seconds. And the magnetic fields that we infer from measuring the spin-down rate, by measuring this, the period and the period derivative of these sources, we infer at least the dipolar component under some very idealized assumptions. We infer magnetic fields at the surface of 10 to the 8 to 10 to the 14 Gauss for these sources. Let's put a few pictures to all these words. This is the famous, the equivalent of an HR diagram or something, but for radio pulsars. On the x-axis here is the pulse period, ranging, like I said, from about a millisecond up to around 10 seconds. And this is the period derivative. And each of these little black dots, that is a known radio pulsar. And you see that the bulk of the radio pulsars sit around a few hundred milliseconds. They're rotating around a few hundred milliseconds. What's drawn here on this, these lines is quite an easy plot, I have to admit, but these lines going in this direction here. These are lines of constant magnetic field. I said you can infer the dipolar component of the magnetic field on the surface under idealized assumptions, etc., by this formula here, which is basically a magnetic dipole breaking period-period derivative and there's a factor in front, and that's what these lines are. So you can see this line is 10 to the 12 Gauss. You can see the bulk of radio pulsars sit in this giant cloud here and have spin-inferred magnetic fields of about 10 to the 12 Gauss. And like I said, it ranges from 10 to the 14, you know, some very weak pulsars down here. The lines going in the opposite direction, these lines are lines of constant age. So that's an age also inferred from spin down. It's called, we refer to that as a characteristic age. It's a spin down age p divided by 2p dot. The reason for the 2 there is a little arcane. But you can see the range of ages. The youngest pulsars, like the crab pulsar, the Vela pulsar, 2 very famous pulsars in the sky, are on the order of a few hundred to 1,000 years old. There's a few of those that we know of. And then going on down, you can see ages 100 megayears up to a billion years. Very old objects. So the other thing that's very important about this diagram is to notice that some of these dots are circled. Those dots, those are binary radio pulsars. So a lot of radio pulsars now are known in binary systems. They're very interesting, obviously. You see some of the slow pulsars are encircled. Occasionally there's slow pulsars, what we call slow, a few hundred milliseconds in binary systems. But you can see the bulk of the binary radio pulsars are in this region of the p dot diagram. They are the fastest rotators. They have very short periods, and they spin down very, very slowly. That combination implies very large ages. These things are the oldest members of the pulsar population, and in some cases the galaxy. And they're also the lowest magnetic field objects in the pulsar population. So this diagram really does tell you quite a bit. So you can, just for the location on the diagram, you have a feeling for the age, magnetic field, and binarity. Here is just collapsing that onto the x-axis, showing you a histogram of the distribution of periods, just to drive the point home a little more clearly. The bulk, there's the bulk, spin periods of a few hundred milliseconds, and then there's this little bump over here of these are what we call the millisecond pulsars. Those are the fastest pulsars that we know of, the majority of which are in binary systems. I see that people are straining their necks, so I wish I could break this. Anyway, the bulk of them are millisecond pulsars in binary systems, which tells you something about their evolution. So this is going to be important because in the Pulsar surveys I'm going to be talking about, one of our big goals is to find more millisecond pulsars. And so it's important to understand why we're interested in them. So first of all, how do we get where do millisecond pulsars come from? Why are they so fast? We don't believe that they're born spinning that fast. The crab pulsar, that's a very young pulsar. It's 33 milliseconds. We think millisecond pulsars, the origin of their very rapid rotation is from an era of recycling. So it's no coincidence the fastest pulsars are in binary systems. We believe that the neutron star went through a period of accretion of mass, matter, and angular momentum from the binary companion, which spun it up to the millisecond rotation rates. So what makes a millisecond pulsar? We think it's a regular pulsar that had a binary companion. When the pulsar was formed, the supernova did not, fortunately or fortuitously in this case, did not disrupt the binary. So there was a companion there that eventually evolved and dumped matter onto the neutron star, and we can study different mechanisms for that happening. These are just different scenarios for binary evolution. When the matter got dumped onto the neutron star, got angular momentum, it spun it up, and in that process, we believe also it caused the magnetic field to decay through a process that still isn't fully agreed upon today, but that's what we observed. And so since they have very low magnetic fields, these are old objects, and once they're recycled, essentially they live forever because their spin down is so slow. They just keep pulsing for billions of years. The current lore says that these objects, the millisecond pulsars, and here clearly distinguished from the non-recycled, young, isolated, largely isolated pulsars, in that the millisecond pulsars seem to be distributed roughly isotropically on the sky, and generally speaking are in circular binaries, because the recycling process also results in circularization of the binaries at a comparable time scale, with degenerate companions typically, but not always with white dwarf companions. So part of this whole lore, this whole evolution of millisecond pulsars, is that they went through a transient X-ray phase during the mass transfer. So when matter was falling on a neutron star, these stars are observed as X-ray binaries. For millisecond pulsars, typically low mass X-ray binaries. So there's a predicted evolutionary relationship between low mass X-ray binaries and millisecond pulsars. Another thing that's just a little bit more background on radio pulsars. One thing that's interesting in a totally different talk that I gave when I came last time about magnetars, if you look at the distribution of magnetic fields of radio pulsars, that's actually the dotted line over here. You see, as I said, the highest magnetic fields we see are around 10 to the 14 Gauss. Whereas, and we dearly love to know if that really falls off. Here's the axis for the radio pulsars, the subject of today's talk. I've blown up, though, these are a different class of neutron stars that I'm not going to talk about, as mentioned very briefly, the magnetars, way fewer magnetars known, but their magnetic fields are higher. And one interesting question is whether there really is a bimodal distribution, really whether he's a separate class of neutron stars, or whether this distribution actually this is just a tail of a single distribution. It's one of the interesting questions. For radio pulsars, the galactic distribution, basically they're confined largely to the galactic plane. So here you can see a histogram of pulsars in galactic latitude. So you see the vast majority are concentrated right in the galactic plane. There are some, as I said, millisecond pulsars in particular at high galactic latitudes. That little spike is the 30-odd pulsars that are known in the globular cluster Tirzan 5.
The previous one, you tried just doing the plotting the current by the, waiting by the spin down here. It's easy to do.
Yeah, no, I haven't done it.
More realistic in terms
of. And this is a plot now looking down on the galaxy. The sun is here, and the galactic center is in the middle. And you can see that these are the known radio pulsars. The blue ones are the slow ones. The red ones are the millisecond pulsars. You see they're really clustered around the sun, just simply because detections are sensitivity limited. In particular, millisecond pulsars, we really generally don't see them out very far away from the sun for reasons that I'll describe shortly. Oh, and I should point out this plot itself is quite model dependent in the sense that it's hard to measure directly pulsar distances. We measure them through their dispersion measures, which I'll explain. It's basically radio waves are dispersed in the ionized plasma, and that's the degree of dispersion of the radio waves combined with a model for how free electrons are distributed in the galaxy allows us to infer a distance. So when I make a plot like this, you should know this is very model dependent. We don't really know the distances that well, except for the very few localized pulsars for which we can measure parallaxes, and there's a few of those. There's I don't know, 20 odd. Another interesting point about pulsars, this is sort of a overall review, but I'm trying to highlight the most interesting questions also that radio surveys that I'm going to talk about are going to address. The pulsar velocity distribution. Pulsars generally have very high space velocities. You can see here different models for the cumulative distribution of pulsars as a function of space velocity. You can see that, for most models that have been proposed and discussed, over half the population have space velocities greater than about 500 kilometers per second. So these are zipping around the galaxy. Presumably this is from asymmetries in the supernovae that form the pulsars. So a small asymmetry in the supernova can produce a large kick velocity, and we think that's the origin of the very high velocity pulsars. Here's an example, just a beautiful example, an H-alpha nebula. It's called the Guitar Nebula. Unfortunately, you can't quite see it. Here's the neck of the guitar, and if you look carefully, you can see sort of the body of the guitar here, maybe not so well in this image, but Martin Van Kerkhoff does some interesting work on this source. There's a pulsar right at the tip over there that's pulling up, and that's traveling at very high velocity indeed. One thing that's interesting is you can see in some models there's this little bump. There's a suggestion there might be a low velocity tail to the pulsar velocity distribution. One of the strong motivators for that is that we find lots of millisecond pulsars in globular clusters where 500 kilometers per second is much greater than the escape velocity. So the question is, why would you have so many radio pulsars in globular clusters? They should have shot out a long time ago, and you shouldn't find any today. So the suggestion there must be some lower velocity population, and perhaps the distribution of pulsar velocities is actually bimodal. And then an interesting question is, well, why would that be? Why should there be two distribution? Why should there be a slow population and a fast population? Perhaps it's two different types of supernova electron capture and quark collapse. It's speculative, but that's one of the issues that's discussed. So I've been trying to highlight, some of the interesting questions in pulsar astronomy. What are the major open pulsar questions? Why do we, ultimately we hope to address? What is the true spin period distribution? And not only that, what is the initial spin period distribution? When a neutron star is formed in a quark collapse supernova, how fast do they rotate? And what does that tell you about the process of quark collapse? So we'd like to be able to infer that from studying the known pulsar population. We'd also like to know the distribution of magnetic fields. And you might just say, well, I thought you just showed me these things. But you have to realize, as I'm going to explain, when we do pulsar surveys, they are heavily, heavily affected by selection effects. Selection effects that strongly select for longer period pulsars, for example, higher magnetic field sources. So when we want to answer these astrophysically interesting questions, we must absolutely consider selection effects in surveys. We'd like to know the mass distribution of neutron stars. This is particularly interesting as physics applications because, of course, the densities of the centers of neutron stars are supernuclear, where we don't know the equation of state. And different models for the equation of state predict different maximum masses for neutron stars. And so by measuring the mass distribution of neutron stars and finding ever heavier masses, we can rule out equations of state for supernuclear matter. Also, another thing we'd love to know is, well, what is the speed limit for millisecond pulsars? So the fastest one is 1.4 milliseconds. That's 716 hertz. How fast can you spin one of these things up? That's already going at about 15. At the equator, that's already 15% of the speed of light. How much faster can they spin? So do sub-millisecond pulsars exist? We would love to know this. It would be great to find one where the surface is going faster than the speed of light, but no, of course, we don't. We have only estimates for the radius. That would ultimately constrain the radius. But long before it constrained directly the radius, it would constrain the equation of state because the matter should have flown apart. And different equations of state predict different maximal rotation rates. So by finding a really fast pulsar, we can also rule out equations of state. It's another way to attack this interesting astrophysics and physics question. We'd love to know the true velocity distribution so that we can understand the origins of neutron stars and whether there are really different types of formation mechanisms for neutron stars, either by quark collapse, electron capture supernovae, or accretion-induced collapse of a white dwarf to a neutron star. And also, just ultimately, we want to know the birth rate of radio pulsars or of neutron stars in general in the galaxy. And what is the total number of neutron stars in the galaxy? And then we could compare the birth rate, for example, with the quark collapse rate, and help to infer things like, how many black holes are there in the galaxy, and what is the maximum mass for producing a neutron star versus a black hole. So these are sort of the questions that we are hoping to answer with pulsar surveys. Now those are the pulsar questions. It so happens that pulsars are actually superb tools for doing a whole variety of other experiments. Pulsars as laboratories for studying other types of physics. I already mentioned equation of state physics, but binary pulsars in binary systems, of course, are famous for being able to do precision tests of general relativity, strong equivalence principle, alternate theories of gravity, and of course have great relevance for detection of gravitational waves. Similarly, binary pulsars are very important for understanding binary evolution mechanisms. I talked about millisecond pulsars being formed in X-ray binaries, so that evolutionary picture it's a nice textbook picture, but really filling in the story, making sure that that actually works, or perhaps some pulsars, like I say, are formed in different ways. There's many different types of binary pulsars. There's neutron stars, neutron star, white dwarfs, neutron star, main sequence stars. There's all sorts of different binaries, and we'd like to know what are the different branching ratios of these. And also, in many cases, we see eclipsing of pulsars in binary orbits, and we can help study stellar winds by looking at those eclipse mechanisms. And, Chris has done a lot of interesting work on eclipse mechanisms in particular. And ultimately, in studying this, we'd love to know merger rates so that we can then constrain, for example, the coalescence rates and what LIGO and advanced LIGO and different gravitational wave observatories should detect. So all of this is using Pulsar's laboratories, and of course then there's connections between topics. We'd love to find a sub-millisecond pulsar, but we'd also love to find a pulsar black hole binary. And the pulsar black hole binary, obviously it would be superb for doing general relativity tests, particularly if we found it in a relativistic orbit. And plus, if I could just register my request with the powers that be in a relativistic orbit exactly edge on, that would be really great. and you laugh. But the double pulsar, which is also quite famous, and Chris could talk your off about it, is within, I forget now, but less than a degree of being inclined, 2 pulsars. And, if you had told me before that was discovered that somebody would find a relativistic double neutron star binary exactly edge on, I would have laughed at you too. So you never know when pulsars are on, what you're going to find. And of course, Pulsars is Laboratories II. You may have heard about this already. We are also in the process of building what's called a pulsar timing array. That is an array, timing long-term, an array of millisecond pulsars distributed around the sky, and using the fact that there's such precise clocks to detect low frequency, nanohertz frequency gravitational waves. And this is a strain versus frequency plot where you can see the expectations for different types of gravitational wave detectors, advanced LIGO, LISA, and here's what a pulsar timing array currently can do. And for example, different sources that can produce gravitational waves in the nanohertz regime where pulsar timing arrays would operate are, for example, supermassive black hole mergers are predicted to yield a detectable signal. Particularly once we have the square kilometer array. So that's a very exciting project. By the way, the North American arm of this pulsar timing array. There's an international pulsar timing array. So there's a lot of pulsars you have to time. It's being done at many different telescopes around the world, the Parkes Telescope, Effelsberg, Jodrell Bank, as well as at Green Bank and Arecibo in North America. In North America, it's called NanoGrav for the, I'll get this around, North American something, Nanohertz Observatory for Gravitational Waves. So NanoGrav is the North American effort to build this pulsar timing array and detect gravitational waves using millisecond pulsars. Okay, so that was my broad science motivation. So I hope I convinced you that finding pulsars is an interesting thing to do. And so hopefully you're wondering, okay, well, how do you find pulsars? So how do we do this? Is we obviously define a survey area. You then point your large, hopefully large radio telescope, and for this, single dishes are really what you want. You could in principle do this with an interferometer, but it is extremely computationally intensive. You want a single dish with as large a collecting area as possible to be as sensitive as possible. So you systematically point your large telescope around the sky, and then you record digitized, very fast sample data. Because of dispersion in the interstellar medium, you can't just sample a wide bandwidth, once, for example, every 64 microseconds, which is what you'd like to do to be able to detect a sub-millisecond pulsar. You want samples that are much faster than, half a millisecond. But that's not good enough. You also have to divide as wide a bandwidth as you can hopefully get to maximize your sensitivity into narrow little frequency channels because of the dispersion. And I'll explain that in slightly more detail in a second. And so you sample typically 1,000 frequency channels every 64 microseconds for some fixed integration time for pointing. For example, at Arecibo, we look we look for 5 minutes on the sky. You then remove the frustrating, deleterious effects of radio frequency interference, and I can definitely talk your ear off about this. Everybody has a cell phone these days. And you disperse at many trial dispersion measures. So the degree of dispersion due to the ionized interstellar medium, it basically, the amount of dispersion of these radio waves depends on how many electrons there are, depends on the column density of electrons. You don't know that in advance, and you need many trial dispersion measures, typically 1,000. So you take all those frequency channels, you disperse at the trial dispersion measure, you run an FFT, and you end up running typically, for 1,000 dispersion measures in a typical survey, so 1,000 FFTs per pointing. And then we do something called harmonic summing because pulsars are not, pulses are not typically sine waves. If it was a sine wave, that would be a single spike in a power spectrum. And they usually have tremendous harmonic content, and you want to take advantage of that. So we actually search in harmonic summing in harmonic space as well. And then that gives us a bunch of candidate pulsars that we examine more closely. Oh, and by the way, these are, when you have 64 microsecond samples for 1,000 frequency channels and more than 1 bit per sample, you would like, bytes, a few bytes per sample. That's very rapidly, you get into very large data sets, and you're doing all these dispersion measure trials, many FFTs. This is a high-performance computing application. This is the idea about that. So you need a lot of computing to do this. And not only that, the discovery rate of pulsars is closely tied to computing power. Highly correlated. So just to drive these things home with pictures, there's a typical pulsar. That's not a typical pulsar at all. That's a really bright pulsar. You can't usually see the individual pulses. They're way below the noise. But let's just pretend, and here's the typical power spectrum where you can see all sorts of harmonic structure, and we sum different numbers of harmonics to try and maximize our sensitivity to narrow signals. This slide is to show you the dispersion that we struggle with. This is another, this is an interesting challenge in pulsar astronomy. You see here, this is now a bandwidth of about 30 megahertz. 30 megahertz from 420 to 450 megahertz. That's actually a small bandwidth by today's standards. So in our Pulsar survey we're doing at Arecibo, we now have 300 megahertz of bandwidth, so it's more of a problem. These are individual frequency channels going across, and what you see is that the pulsar signal is highly dispersed. So that, I think it's actually the blue pulsar, but never mind. The high frequency signal arrives first. And it follows a 1 over frequency squared law. That's the cold plasma dispersion law. And you can see that the degree of delay from the high points on your highest frequencies to your lowest frequencies over even a relatively small range of bandwidth can be many pulse periods. You see this one wraps around many times. If you didn't correct for this effect, you would totally smear out your pulse. You would try and sum all of these and all the power would be uniformly distributed. You wouldn't detect the pulsar. Whereas if you know the slope, you can just correct for it in software. You record each of these and you then de-disperse. You align them according to 1 over frequency square law, and there you get a lovely pulse. So as I said, this slope is proportional to the column density of electrons in the interstellar medium. So it's different from pulsar to pulsar. So when you're searching, not only are you searching, you don't know the period in advance. you'd love to know that. You don't know the period in advance, that's why you do an FFT, but you also don't know the dispersion measure in advance. You have to search in this slope space as well. And before, when I showed you the plot of distribution of pulsars in the galaxy, I said the distances are very model dependent. This is a typical model. This is the Cortez and Lazio NE 2001 model that we all rely on presently. Again, looking down in the galaxy, here's the galactic center, here's the Earth. These are contours of constant dispersion measure. So you can see that this is an attempt at modeling how the electrons are distributed in the galaxy, and we rely on that by measuring the dispersion measure in some direction. We say, 300, well, it's about 5 kiloparsecs. But the uncertainties are typically 30% for this method. There's other difficulties in finding pulsars also. I should just say that the dispersion effect is in principle completely correctable by just having infinitely narrow frequency channels, and many of them. There's always some residual dispersion because each channel has some finite bandwidth, so there's always a little bit in there, and that in some cases limits how fast a pulsar you can find because there's some residual smearing.
Question: how do you map the slope?
So it's brute force. We take the raw data series, we try one slope, we redisperse it, we do a time series, and we FFT it. We then take the raw data and we redisperse it at a slightly different DM, and we FFT it. And so we go over 1,000, sometimes more trial dispersion measures.
And then what are you doing this?
There are tree algorithms that can make it faster. You can subband your data. You can break it into chunks and you disperse at smaller chunks. And the other thing, you can also, your DM step size can increase as you get to higher dispersion measures because the broadening within a pulse will dominate over the error that you make by making the steps too large. There are lots of tricks, but conceptually so you can correct in principle for that dispersion. But one thing that's harder to correct for is pulse broadening. So you have a pulsar in a telescope, and the interstellar medium has electron density perturbations. So the DM is proportional to the total column density. You don't care how it's distributed. But if it's distributed in clumps that are moving around, that actually scatters the pulsar radiation and causes pulse broadening. So that scattered light from some blob over here sends the pulse, some radiation back, but that results in a time delay that causes pulse broadening and a scattering tail on the far side. So this is a strong frequency effect, but at low radio frequencies, the pulse is very heavily broadened, whereas at high frequency, it actually goes to the fourth power frequency approximately. So this drives you to wanting to observe at the really high radio frequencies where the scatter broadening is minimal. Unfortunately, pulsar spectra, radio spectra, shoot up at low radio frequencies. So you lose pulsar flux. They're weak up here, unfortunately. They're really strong down here, but then you're scatter broadened. So every survey, you figure out what you're looking for, and you choose your survey on the basis of that. Now then, there's also the issue that some pulsars are in binary systems. So a pulsar that's in a binary, of course, so if this is, a power spectrum of this is an isolated 3 millisecond pulsar, and it just offsets, this is an offset, this is the bin that it should be in. The isolated pulsar, you do an FFT, you see a spike, and maybe you see harmonics. But if the pulsar is in a binary system, in this case, the binary, it's a one-day binary. It's a 3 millisecond pulsar, and this is, say, a 2-hour observation, so it's quite a long observation. You can see the Fourier power per bin dropped from, it was actually unity in the previous plot, to 2%. So what happens is the pulsar, because it's actually accelerating during your observation, the frequency is changing because Doppler shifts the binary. And so that power gets spread over many Fourier bins and reduces your sensitivity effectively. So what we do, we also not only do search in dispersion space, not only do we do FFT, but we also search in acceleration space. So we look for linearly changing frequencies. So that actually is what dominates our computing time, is acceleration searches. It's not as important for a survey, the 2-hour observation is quite long. And this is you know, for a one-day binary, you see significant smearing. But, you know, the most relativistic system we know of is a 2.4-hour binary. The 2.4 hours, you know, if you did a 2-hour observation, you would never detect it like this. You know, and in surveys we try and do, you know, it's a trade-off between getting as many pulses as you can and as much flux by maximizing integration time, but you want to also minimize it in order to avoid losing all the most interesting binaries. You want to find the half-hour binary. So, you know, it's a problem. Anyway, finally, Presto, you get, that's actually the name of the software that we use, written by Scott Ranson. This is a Pulsar candidate plot. You can see here, this is all sorts of little diagnostics that tell us if something is a pulsar. This is, I look at that, I go, oh, that's a pulsar for sure. This is the phase versus time plot, and you can see a nice vertical line, and this is the sum. Here it is in the same thing, phase versus radio frequency. Since they're broadband sources, you expect to see a line, and you see a line there. You can see some narrowband radio frequency interference in there. That's some TV station or something. We also look to see, make sure the signal, this is a dispersion measure. We'd like to see a nice peak in dispersion measure space. Anyway, okay. So that's pulsar surveying in a nutshell. Why don't I mention, so very quickly, of course, we want to find this holy grail object. We want to find the black hole binaries. We want to find the sub-millisecond pulsars. But the main pulsar survey science comes from population synthesis studies. So, as I said, there's huge selection effects, as you can imagine. Sensitivity depends sensitively on the period, on the dispersion measure, location in the galaxy, the integration time, especially for binary pulsars, even the pulse shape. So the way we understand pulsar surveys is by forward-folding models of the population through a simulated survey. So first of all, just to show you, these are some sensitivity curves for different types of pulsar surveys, or different pulsar surveys. Here's period on the x-axis and minimum detectable flux on this axis. And this is, you can see, as a function of period, you lose huge sensitivity as you go to shorter periods because of dispersion smearing, because of pulse broadening. So the different lines are for different dispersion measures. So you hit this wall when you want to find millisecond pulsars. It's hard. But the main point here is that it's complicated, the selection effects. So we'll simulate a virtual galaxy of pulsars, and then we'll assume model parameters like an initial spin period, magnetic field distribution, spatial and velocity distributions, a luminosity law, you know, how bright is the pulsar given its period and period derivative, a beaming law, what fraction of the sky does that beam actually intersect, a distance model. All of this you assume, you create a virtual galaxy of pulsars, and then you survey it with, you know, in the computer with a telescope given some survey parameters. And so examples of this, I did a study of Park's multi-beam survey. It was a big survey that discovered over 1,000 pulsars with an undergrad, then undergraduate, Claude André Fauché-Giguère. And we find all sorts of things. But, for example, modeling, this is only valid for slow pulsars doing this. To try and model the galaxy from millisecond pulsars is much more complicated because they went through this complicated era of recycling and binarity. That's a harder problem, although we're trying to tackle that. So actually I have a postdoc right now at McGill, Antoine Bouchard, who is trying to simulate millisecond pulsars. If you're interested in how we're doing that, I can tell you later. But anyway, just to show you what a great job he's doing so far. This is a P dot diagram with this red and blue points, and you can try and guess which are the simulated ones and which are the real ones. You know, it's hard to tell, so he's come up with a pretty good model in this case. Yeah, and by the way, simultaneously trying to simulate the galactic population of low mass X-ray binaries, because you'd better get that right also. And from this, we're hoping to learn the total number of millisecond pulsars in the galaxy. Okay. So that's why I told you why we do surveys. I told you how we do surveys, how we understand the gross output of the surveys. Now let me tell you about the surveys themselves, the ones that I'm working on, that I'm heavily involved in. So there's the PALFA survey. We're surveying the galactic plane with Arecibo, the largest telescope in the world. That's located in Puerto Rico. It's an international consortium with about 30 members. I'm the PI of this consortium. We're doing it at 1.4 gigahertz. We have 5-minute pointings, 64 microsecond samples, and as I mentioned, 300 megahertz. And by the end of the survey, we'll have collected about a petabyte worth of data. This survey is enabled, so Arecibo, because it has such a large aperture, of course the beam size is very, very small. So to be able to cover large areas of the sky with the alpha receiver at 1.4 gigahertz, that's 20 centimeter radiation, you need a multi-beam receiver. This is a multi-beam receiver. There's actually 7 pixels on the sky simultaneously, so 7 independent pixels. This is what the beam pattern looks like on the sky. So because we have this factor of 7 increase in survey speed, it makes this slow but feasible.
Who built it?
This was actually built by the Australia Telescope National Facility engineers there, and then brought to Arecibo.
The same people who did parks?
Yes, the same people who built the parks. There's the PALFA consortium. I'll just highlight a couple of names. McGill postdoc Ryan Lynch and the McGill grad student Paul Schultz have done a huge amount of work, as have many members of this consortium. This is where we're surveying. This is the Arecibo visible portion of the galactic plane. So Arecibo being this huge dish that's in the ground that's not steerable. The dish sits in the ground. It's a spherical reflector, so you can move the suspended antenna to get some range of declination, zenith angles. But this is the part of the galactic plane that's visible from Arecibo. So what Arecibo is to prove at is sensitivity. It can go very deep, but it can't see most of the sky. In fact, if you look down on the galaxy, here's the sun, here's the galaxy, the orange, yellow shaded regions are the regions of the galactic plane that Arecibo can see. And so just ignore the blue points for the moment. This is our approximate sky coverage so far. You can see we're nowhere near complete the survey, even though we've been doing it since about 2006. It's slow because it's a tiny. Each of these little gray dots that you can see is a cluster of pointing. So it takes a very long time to survey this, particularly when the galaxy is only visible for a few hours per day because of the pointing constraints. So that's a problem with Arecibo, but on the other hand, what Arecibo is superb at, and the PALFA receiver in particular, and the spectrometers that we're using, these are contours of constant dispersion broadening. So you can see that you can go very far out before you get this blue line. That's dispersion broadening of half a millisecond. That's very short dispersion smearing time. What that means is we have tremendous sensitivity through millisecond pulsars to up to far greater volumes of the galaxy than we've had before. So P-alpha is really good to finding highly dispersed millisecond pulsars, which gives us a far greater sensitivity, volume of the galaxy we can find pulsars in. This is again the minimum flux, minimum detectable flux for the survey against spin period here. You can see different current surveys going on. Hit run, that's the survey being done at Ethelsberg and Parks currently. GBT, I'll talk about, if I have time, I'll talk about that. And P-alpha, the survey you see is by far the most sensitive survey ever done for pulsars.
About 90 kilofibers.
That's about right. Yeah, that's about right. But we don't have as much sky coverage, so that's good. So as I said, this is a very compute-intensive project. We are making heavy use of the Gilliman node supercomputer as part of this CLUMEC consortium, part of Compute Canada. This is located at McGill. We sometimes get as many as 2048 processors, and this is an embarrassingly parallel process, so we just need serial processors for those of you who are into HPC. The data set is actually being processed at 2 independent pipelines, so one on the Gilliman computer at McGill, and another by the Einstein at Home consortium. So if you feel like processing and searching for pulsars and P-alpha in your spare time, then you can. You can go to www.einsteinathome.org, and this is you know, it's like the SETI at home kind of program. You can download data and in your computer's spare time, use up those CPU cycles to search for pulsars. And it actually works, but I'll tell you that in a second. Total discoveries versus the PALFA discoveries so far, we're up to 101 pulsars in the PALFA survey, and this is the number of pulsars discovered versus year. This is when we actually increased our bandwidth by a factor of 3, and increased, this is when Gilliman came online, increased our processing power, so suddenly the pulsars are just popping out. This is projected through the rest of the year, these are the locations, as you guessed from the time I showed you this plot before. These are the locations of the pulsars that we've discovered. You can see we're going quite far out now in the galaxy, particularly for millisecond pulsars. So the millisecond pulsars are the ones that are really good for detecting gravitational waves and for all sorts of other studies. You can see that the black dots are the known pulsars, and the blue dots are going way further. It's the newest development of the galaxy that we're sampling. You can see the same thing in this plot. This is period and dispersion measure along the y-axis, and you can see the the DM to period. We're going into far greater dispersion measures, generally speaking, than the bulk of the population. So very quickly, some highlights. So it's great to get all the survey data, but in doing pulsar surveys, there's the two modes of scientific discovery. There's the overall survey results, which tells you about the population, and then there's the jewels. There's the holy grails, the individually interesting objects. So the first millisecond pulsar we found was actually a total shock. This is a 2 millisecond pulsar, a very high dispersion measure. This was actually the record breaker in terms of dispersion measure over periods. A very short period pulsar and high dispersion measure. But what was particularly amazing, and you can see it here, just absolutely lovely, nice bright pulsar, could not have been found without P-alpha because of the huge smearing. In fact, that's the width of that pulse is dominated by dispersion smearing. But what was amazing is that it turns out it's in a 95-day binary orbit that has a very high eccentricity. And if you were listening carefully when I was talking about the origin of millisecond pulsars, I said they're all in circular orbits. And that's just because we all know that they are born and they're recycled in this X-ray binary phase that rapidly circularizes the orbit. And so you never find millisecond pulsars in eccentric orbits, except possibly in globular clusters, because the density of stars there is so great that you can induce perturbations or have exchanges or all sorts of interesting activity there. But this is in the galactic disk, in the galactic plane. You should not find it. When we found this, it was, we thought it was a mistake. But it's not. It's a highly eccentric. And so the formation mechanism is quite unclear, and we discussed this quite a bit in this paper by Paulo Freire. We think that the only way to form something like this had to be in a triple system, and it's actually quite a complicated evolution. I'm going to refer you to this paper for the speculation how it could have formed, but you'll read it, you'll see if you believe it. You might think, well, what if it was formed in a globular cluster, eccentric, and then somehow spat out of the cluster when the cluster passed through the galaxy? One interesting thing that Paulo and that we did was to measure the proper motion, and also by observing the companion star, measure its radial velocity, and determine its space motion in the galaxy, and then integrate it backwards. It's something that Paulo did. The red line is his calculations of the orbit that the source had to have, and in particular note, so the blue, green, and cyan lines are other pulsars. The red one is this pulsar, 1903. What Paulo finds is that given its present velocity, integrating backward, it had to have always been confined to the galactic plane. So it's very hard to see how that could have come from a globular cluster, which is why we have to resort to interesting third-party effects. But not only that, I mean, what's interesting here is that this is a millisecond pulsar that is only going to be found in the galactic plane. Is that related to the fact that maybe it had a triple? The other thing I previously said when I was talking about millisecond pulsars is that they're isotropically distributed on the sky. because the reason for that is because they're really old population. They're born of pulsars with high space velocities. A lot of them get shot out of the plane, and they're really old. They're billions of years old, so you expect them to be all over the sky. You don't expect to find a lot of them in the galactic plane. The fact that this one is confined to the galactic plane, the first time you have sensitivity for millisecond pulsars in the galactic plane, you think, we stumbled on something. It was the first one we found. We've now found lots more MSPs. I think our number is, I forget now, something like 15 millisecond pulsars. And in a paper by Julia Deneva, we report on long-term timing observations of 2 more PALFA MSPs, both of which have very low proper motions and low velocities perpendicular to the galactic plane. So neither is detectable velocity vertical to the galactic plane, just like 1903. So for the 3 millisecond pulsars for which we have velocity information, all 3 are basically stuck in the galactic plane. So it kind of suggests maybe PALFA, because it's, it's the first time you've been able to really look to great depths in the plane, maybe we've stumbled onto a new class of millisecond pulsars. And maybe this has relevance to the fact that the velocity distribution is hinted to be bimodal. Maybe these are a low velocity class of pulsars that form these millisecond pulsars. Or maybe it's just a selection effect in that PALFA looks only in the galactic plane, so you're going to tend to find things that are found in the galactic plane that only are in the galactic plane. But we're fine, as I say, we have lots more millisecond pulsars. We're going to time them all, measure all the proper motions. We'll know the answer to this soon. I should also just mention the Einstein at home. So if you want to go out and find millisecond pulsars, you can. And in fact, there's now been multiple pulsars found with the Einstein at home projects. I mean, there's something like, I forget, hundreds of thousands of computers around the world who are dedicating their CPUs to this as a screensaver. The first one that was found is an interesting 24 millisecond binary pulsar. The first pulsar discovered by Global Volunteer Computing. You can see the details. There's the pulse profile. That's how they look at their data. And here are the discoverers. They're just, that's them. Here they are. Now, so that's one. I described one of the jewels that we found, this eccentric millisecond pulsar. In terms of population studies, we're just getting started on this. Here's an interesting plot made by Jim Cordes from our collaboration. Galactic longitude, the red pulsars are previously known pulsars, and the blue pulsars are PALFA pulsars. The black line is the maximal predicted dispersion measure along that line of study, along that longitude. So that's what the NA 2001, that's what presently the best model for the electron distribution in the galaxy that we use to determine distances to all pulsars. That's what it predicts. And well, Jim notes that there's this interesting little dearth of pulsars right in this range here, and is wondering if that's some sort of interesting effect going on in the galactic distribution. The numbers are still small. Is that statistically significant? Our coverage is far from complete, as I showed you. So it's just this flavor for what we're hoping to do. One thing that actually is a little disturbing about PALFA is the pulsar paucity. We found too few pulsars. Antoine Bouchard, who's doing these population synthesis models that I showed you earlier, he predicts about a factor of 2 more PALFA. We found 100. He said we should have found 200, or maybe even a little higher than that discoveries so far. And he makes that prediction on the basis of models that correctly post-stick the number of pulsars found in previous large-scale pulsar surveys, like the Park-Longitude survey. So if you take the Park-Longitude survey and you model it, and you come up with the best model for pulsars, he predicts PALFA should have found more. So now PALFA is very sensitive to a narrow range of longitude, so maybe we're learning something about the distribution of pulsars at galactic longitude. Maybe we're learning something about pulsar luminosity law or the distance model. All of these things are things we're trying to study now. Unfortunately, there's a giant gorilla in the room. This gorilla is saying, have you properly handled radio frequency interference? And the answer is no. We are doing our best. This is a very, very hard problem, and I could stand here and give you an hour-long talk about the different types of radio frequency interference that we see, how and the different steps we're taking to try and mitigate it. We're currently reanalyzing all the PALFA data with a brand new set of techniques for getting rid of RFI. It could be that we're just missing a lot of pulsars because of everything from radars in the Caribbean. There's a lot of drug trafficking, I understand, in the Caribbean. There's Coast Guard, huge frequency swept radars, just it's a big problem.
So do the models incorporate RFI?
No. So this is
problem
exactly
is in the model rather than in your data analysis.
the model does not incorporate RFI, and this is, we have to figure out how to do that.
Life is short.
Well, yeah, okay, well, maybe you don't, but if you do want to understand the output of your survey, so you could either just live with doing pulsar surveys to find the black hole binaries and the eccentric millisecond pulsars, but if you want to understand your longitude distribution and your luminosity law, you've got to somehow handle this problem. I had some nice examples, but I wanted to, I don't have much time left. I thought I wouldn't have a lot of time left, but that's what I started. I have like 4 minutes. So I'll just very quickly mention, we're doing also another survey in a radio quiet zone. So the Green Bank telescope is the Robert C. Byrd 100-meter telescope in Green Bank, West Virginia, the largest fully steerable aperture. This is when we can steer the range of the galaxy that we can see. You can see it for much longer. It's fully steerable. You can see this is the area of the sky we're looking at, the North Celestial Cap, a huge area. Compare it to what we can do with Arecibo. Yes, Arecibo is superb sensitivity, but very, very narrow. We can't, it has such a tiny beam, you can only look at a small area. Here, the aperture is smaller, we're at lower radio frequency, in this case 350 megahertz. The beam is bigger, we can cover vast areas of the sky with the survey. We did sort of a prototype survey. The GBT was down for a track refurbishment. There's an azimuth track that it rotates on. That was had to be refurbished, and the telescope was stuck. So we actually did a pulsar survey with a broken telescope this is a few years ago, by just letting the sky drift overhead and fast sampling the data, and that was incredibly productive. This was the GBT Driftscan Survey. It was sort of a precursor to the large-scale survey we planned to do, just to see what we could find. So the dish was stuck in zenith, the sky drifted overhead. We collected 134 terabytes of data at 350 megahertz, covering 12,000 square degrees with lots of gaps. And we found 24 new pulsars. Let me tell you about some of them. For those of you who know what a rat is, I don't have time to explain in 4 minutes, but we found a pile of rats. These are, okay, ask me after if you care, but this is interesting that we found comparable numbers of rats. I'm not going to talk about this one. I will talk very briefly about the one, we have a 2.7 millisecond pulsar in a hierarchical triple. That's what we're working on right now. Scott Ransom is working on this. This is a velocity curve. This pulsar has an inner companion. It's probably a white dwarf on a 1.68 orbit. But on top of that, you can see now that if this is here a few months of data, the pulsar period, this is pulsar period versus time. A huge effect, that is, this is not spin down. This is Doppler shift due to an outer companion in a 327-day orbit. We're just working on this now. Very interesting result for the GBT Driftscan Survey.
Is that the first pulsar triple?
There's one other pulsar triple in a globular cluster. This is the first one not in a cluster. And maybe the PALFA source I told you about is from a triple, but it's currently not. This one is currently in the system. So interesting for three-body dynamical theory. Very quickly, this is a really interesting pulsar. I really wanted to be sure to mention it, so really quickly. Let's cut to the chase. Okay, well, okay, based on observational work by these people, everything here is preliminary. Okay, so don't freak out on me. I did this talk at a Harvard GR conference, and 30 seconds after the end of the talk, I got like an email from Jim Latimer going, I heard you talked about a massive neutron star in a relativistic orbit. So that's the punchline. We found a massive neutron star in a relativistic orbit. 39 millisecond pulsar, the orbital period 2.4 hours, only a few seconds longer than the fastest known orbit, which is the double pulsar. The double pulsar is 2.4 hours. This is just a few seconds longer, so it's highly relativistic. It has a white dwarf companion that's quite bright. So Martin Van Kerkwijk has been collaborating on this project. The mass is very well, or fairly well determined from the spectrum and the model. So there's a gravity and temperature measured, and from spectral models, the white dwarf companion is known to be in this range of masses, although this is something we're discussing. The white dwarf has huge Balmer absorption lines that show clear orbital Doppler shifts at the 2.4-hour period. There they are. This is huge. So this is the velocity curve for the white dwarf. Okay, the white dwarf, you can observe it. This is a 2.4-hour orbit. Very clear. You see the white dwarf's motion. This is what we infer from pulsar timing. That's the green line. So from your, astronomy 101, you can get the mass ratio immediately, and there it is. Mass ratio 11.7. So if you know the mass of the white dwarf from models, and you know the mass ratio, then you know the pulsar mass. And currently, so I should have, preliminary. The mass of the pulsar here is in this range with 99% confidence. So it looks like a very, a massive neutron star. This is, quite relevant to equation of state models. It is in the same range as the recently reported 1.97 solar mass Norris-Dahl paper neutron star. That was on the basis of Shapiro delay measurement. But what's interesting, so the comparable masses, this one even maybe more massive, but it's the first massive neutron star in a relativistic orbit. And so there's a whole bunch of new general relativity and relativistic gravity tests that you can do.
You be able to measure the moment of motion.
The moment of motion. Well, right now, what can be done and what has been done is the best limit yet on dipolar gravitational waves. So you have a massive star, and you have a white dwarf next to it with a large mass ratio. You can do that, and also in alternative theories of gravity, there is coupling, much stronger gravitational coupling to the matter in the neutron star. You could set limits on the parameters of tensor scalar theories of gravity. So there's an orbital period derivative measured for the system that is consistent with general relativity. I've run out of time, so I'm talking really fast. I apologize. In any case, you can set limits on various parameters in tensor scalar theories that are much more stringent than previous.
What's the magnetic field strength? It's
a typical millisecond, recycled millisecond pulsar. I don't remember the exact, it's like 10 to the 9 or something like that. The other thing that's interesting, well, I've run out of time, but I just want to say that it's interesting for gravitational wave detection also, because the limits that you can set given the measurement of the orbital period derivative and testing GR and ruling out these tensor scalar theories allows you to set limits on the difference in the cycles. So this is now, if you merged a 2 solar mass neutron star and say a 10 solar mass black hole. Okay, so now we're talking in the regime of massive neutron stars, where these tensor scalar theories might be most important. This is now, in general relativity, this is the number of cycles that you would have during this merger up until the last stable orbit. This is, in a tensor scalar theory, there would be some deviation, particularly in the final throes of merger, and the blue line is the difference. So you can see now, thanks to the limit from this system, you can limit the number of, this ring down, this plot here, you can see you predict a shorter ring down in the tensor scalar theories, but you can set a limit on the differences in the number of cycles between the mergers that's less than, here's one cycle. And you can do that, anyway. So anyway, it's good news for gravitational waves because the binary pulsar is useful. We can test tensor scalar theories, and it was true for low mass neutron stars. And now we know for high mass neutron stars where this coupling and between the large fractional binding energy of the neutron star, you might expect these tensor scalar theories to matter more. It's good news for calculating templates because it suggests that the post-Newtonian formalism should work well for massive neutron stars as well when coalescing neutron stars. So I won't talk about the many pulsars we've already found in the real North Celestial Cap survey. I will just conclude by saying pulsar surveys, they're important for a variety of reasons, which I hope I've convinced you of. They're yielding, so the PALFA and GreenBank surveys are yielding lots of fruits. Interesting constraints on the total population, all sorts of interesting millisecond pulsars, interesting binary pulsars, high mass neutron stars, relativistic orbits, all sorts of things. Thank you. That's it.
All right, thank you, Vicki. So we're going to have cookies after this upstairs where you can talk more with Vicki, but right now there's a couple of questions that people have.
Alright, so your surveys were at 1.4 gigahertz LC, but you just said that pulsars are much quieter at lower frequencies, and your beam gets bigger. Why wouldn't you want to do this at?
Because then there's the pulsars are scattered. So millisecond pulsars get scattered broader than the plane. So if you want to look far out in the plane, the lower frequency you go to, the pulsar you lose sensitivity.
But again, I didn't follow that because I thought people say it was coherent dispersion. You can disperse anything, and anyone can.
Yeah, for coherent dispersion, you need to know the dispersion measure in advance. That's for when you're timing.
It's a computational problem of trying to do
Yes.
that.
Oh, absolutely. If you could, yeah. Today it is hopeless to imagine a large-scale survey, large-scale pulsar survey using coherent dispersion. It's impossible. If the baseband sample your entire bandwidth. Yeah, no, that's hopeless.
Is PTA going to be sensitive to big changes in the end, physical changes in the end, the fact that it expanding ionization zones?
Sure. So a millisecond pulsar, so this is actually in my PhD thesis, you can see a lovely plot of dispersion measure versus time for individual millisecond pulsars. You see changing, it's at a very low level, but it's highly significant. That's actually a problem for the pulsar timing array. You absolutely have to, if you can do the pulsar timing array, you must time it at multiple at least 2 radio frequencies to subtract off that effect. Otherwise, you think you're detecting a gravitational wave and you're just detecting some ionized cloud. So absolutely, that's a big effect.
So you mentioned black hole neutron star bindings, which would, of course, be really cool to see. What are the expectations on event rates for these systems? Is there any reasonable chance of finding one? Should we already have seen one? Would we have to search 100 more years to see one?
Right. Okay. So there are some simulations that have suggested that, roughly you find one pulsar black hole binary per 1,000 pulsars. So we're at 2,000. So we're kind of due in that case. And they're quite rare compared to neutron star binaries, by the way, because in the standard picture of a neutron star black hole formation, the more massive, so you have a binary, which you need 2 massive stars to have a binary, one of them, the more massive of the 2 explodes first and forms a black hole. And there's nothing to recycle the pulsar once it's formed. And so the pulsar is a slow pulsar that dies after 100 million years or whatever. I should have commented there's a graveyard there. So you can't detect them after 100 million years. Whereas if you had something to recycle the pulsar, it would live for 1 billion years and have a much greater chance of finding it. So that's one argument why they're going to be relatively rare. I mean, on the other hand, there's at least one, and maybe more than one, slow pulsars in relativistic orbits. And the idea is that if you start, this paper, for example, by Voss and Thomas Torres, where if you start with 2 massive stars, but one loses mass by dumping it onto the other one first, then you can form the neutron star first, and then then you can recycle it, but the second star has a mass enough on it to turn to a black hole. So there are formation mechanisms that have suggested you could find a recycled pulsar with a black hole. And then, of course, maybe in a broader cluster. That's the other place you can hope to find it. So the answer is, you gotta look. Go.
Do we have any other questions for Vicky at this time? Okay, so we can carry on conversation upstairs with cookies, and I have space for one more person to join us for dinner tonight. So come and talk to me if you're interested. And let's thank Vicky again.
I was at a conference.
So far, it's been a revolution.
Hey, Sean, how are you?
I'm not, but my statement is a real far.
Okay. Because I was at a conference, someone over there saying they consequence of RS.
Well, so here's the problem with RRAS. So I think RRAS are incredibly important.
I think they're important.
And okay, maybe they're just, not, intrinsically interesting from a physical point of view.
Oh, no, they are.
Oh,
no, they are.
Okay, good. So you're going to tell me that. But
Well,
also,
if I can explain it,
well, but just from a population point of view, previous surveys were not sensitive to them. And
So
here's
why
a-
do you see so many in the Green Bank and not in the Harrison Black Cat?
Oh, because of it's really hard to find RRAS, and we're working on it, but yeah.
Green Bank is just not way to be able to find.
Yes, it's a huge factor that I think it's a real issue. But doing me said like short. I'll tell you because it's actually kind of fun to figure out clever ways to pick up the pulsars. So you listen to come up with things. It's not like ooh, they all appear. It's like it's wonderful.
Sure, but doing population synthesis, doing the kinds of RFI makes me